Okay, let us learn how to create a study from um, FreeCAD using an imported object. So you can create an object 2D or 3D from any other software. In this case, we can use AutoCAD to create the solid. If you don't want to create the solid on FreeCAD, or because you already have the object somewhere else. So let's just create a solid. In this case, we just want to create something that we can import. So this is going to be a circle. We want to create a column, and let's say the diameter is 1 inch. Remember that you have to set up your dimensions from the beginning if you want inches or if you want millimeters. Since I have inches, then I just have to remember that 1 inch is 25.4 millimeters. So this distance right here is a circle of diameter 25.4 millimeters. To create the solid, we already know how to do that from AutoCAD. Let's go ahead and use a different view and let's extrude the part. And we're gonna say it's about 100 millimeters, so that will be close to 5 inches. Enter. And let's change the view to a solid view. Okay, so now we just need to save this as a part that is compatible with any other format that we can import to FreeCAD. Remember that one easy um, one format to export is IGES, so it's not under open, it's actually under export. So go ahead and click on export, and other formats is one option. Other option is file and export, and right here you can choose IGES. And you're not done. You have to select what parts to export. In case you have many bodies, you can just export the parts that you select and enter. And then you have this um, sign that tells you the parts are exported. So in case you have export parts from other software, say SolidWorks or Pro Engineer, as long as you have something in IGES or Parasolid or something that is a volume representation, then you can do an FEM analysis. Because you have an STL or something that is just a surface representation, then that is good for 3D printing because you only need the surface of the body to cut or to extrude or to inject. But for a physical analysis, you do need the volume because you're integrating over a volume if you look at the equations of the governing equations of your physics. So as long as you have a volume, in this case is IGES, a good format. And this is a volume of a cylinder, which could be a column, for example. All right, now that you have your part, you go to FreeCAD. And on FreeCAD, we already know what to do. We go to New, we go to File, Import. Once you find and import your part, then you can do the analysis the same way. So go to your tab and find finite element method. And then it's going to bring this window this ribbon right here. You have to click on analysis to activate your analysis. And if you see under analysis, you have your solver options, but you don't have anything to solve. Remember that you need three things. You need material properties, you need a discretized domain or the mesh, and you need the boundary conditions. So let's start by assigning properties. So this circle is the properties, the material properties, and you can create your own or choose something from the library as long as you have the density and the modulus of elasticity, Young's modulus, and the Poisson ratio because you're doing linear elasticity. All right. If you decide to go to thermal analysis as well, then you have the thermal conductivity and the expansion coefficient and the specific heat. So those are the minimum properties that you need, the minimum amount of properties that you need. All right, so right here is telling you to choose a solid or what parts to assign the properties. And we want to create a solid because we want the volume to be the same property. All the volume needs to have the same properties for this study. And if you add, it's going to say solid and the name of the part, even though I just selected one surface. That's why it's important that you have solid instead of phase, because if you choose phase, then it's only going to select properties for this, and everything else is going to be void, and it's not going to work. It's not going to be air or anything. It's going to be unassigned, and it won't work because the equations require material properties. Okay, so we have the first thing, the material properties. We need the second thing, which is the boundary conditions. So let's go ahead and select, now we do faces, and we're gonna do, the column is gonna be fixed or soldered to say the ground, or we're gonna be buried on the ground. So we're gonna choose this property, this face, and we're gonna say okay. And then we're gonna say that we're gonna put a force on top on this face. So let's choose either pressure or force. Let's just go for force. The difference is force is going to be in newtons, the pressure is going to be in pascals. So let's go ahead and say that we want to have this phase is going to be 100 newtons, and we want it to be compressing, not stretching. So reverse direction, and okay. All right, we have the boundary conditions. We're not going to have anything on the radial direction because it's going to be a column, not fitting. But you can do your study however, whatever you want. In this study, we're just going to do a column. Okay, the last thing we need to do is, I'm not going to do any thermal behavior. It's going to be room temperature, so it's not going to change temperature or anything. But what I do want to do is the mesh. So once you click on the geometry, the mesh options are enabled. And then remember that this is the important part. The radius, or better, the diameter is 25 millimeters. So we want to have a maximum size smaller than that. So let's say 5. And the minimum is going to be 1 millimeter. That is going to be the size of the element. You learn more about that when you take your finite element classes. The element dimension is going to be assigned from shape. So it's going to be capturing the curvatures, and I'll show you after we mesh it what is the meaning of capturing the dimensions from shape. And the order, just keep second because it's much more accurate than first. It's a second order approximation to your equations. Okay, and then we're gonna apply. And this is the mesh. That was pretty quick. Okay, so if you notice, it's from shape is because it's capturing the nodes of the elements, is capturing the shape of the geometry that we have. Okay, if you wanted to refine this, you'll notice that it's going to be much more accurate on the edges. All right, so the concept of finite elements is that it's going to solve the physics of deformation at every point, and all the points are connected. Notice that you have, wherever you're connecting, that is going to point, there's going to be a point where you're solving your deformations and your stresses. And later, it's going to be extrapolated to the whole area of the element. Again, you'll learn more about that in your finite element class. Okay, now we have the mesh, the boundary conditions, and the material properties. Now we're ready to study our column. So you can do a static analysis, which means that whatever that load is will be applied, and we just want to know the end state, if it's going to break or not, based on our elasticity modulus. or thermomechanical, which in this case we don't want to do because I didn't assign any thermal properties, but you can. Buckling, which is the deformation shape, if it's going to buckle because of these stresses. We don't need to check the mesh because it's a good mesh. And that is usually for a complicated geometry when you check the mesh. And let's do a frequency study. So we can do eigenvalues and see what at what frequencies is this, if this is going to be installed as a bridge, like a column for a bridge, then those frequencies of cars passing through, creating that the vibrations, then this could be a frequency study. So in that, you have to decide what type of study is going to be worth studying. So first of all, we have to write the input file, and the input file is going to be used for running the calculation. So you run the calculation, and then you can see the time that it takes to compute. This time is going to vary depending on the hardware, the computer that you have, the amount of RAM, the type of processor, and down here you can find your input file in case you want to bring this file and copy, send it to your colleague, to your boss, to your friends, because this is going to be the study basically. Instead of carrying the whole study, you just carry the input file, and then you can solve it later on using the same solver or using a different solver like Abacus or SolidWorks or something, or Nastran, something that takes an input file and solves it. So this is a very useful um, input file. As long as you have access to the input file, you can redo the study and change the material properties from the file. Check the last video and you'll see how to access the input file, and you can change the density. You can change mostly anything, even the mesh, the boundary conditions, the amount of boards that you put. All right, once it's solved, in my computer it took 43.8 seconds with no errors, and it's gonna give you a data file, which is the answer. You can also carry that with you, but this is not gonna be something that you can modify. The input file you can, the data file is not something that you will get to modify. This is the solution to your elasticity equation, which is a second order partial differential equation. All right, so let's go ahead and see our results. So we did a frequency study, and in the frequency study, you're gonna have something called eigenmodes. You can go ahead and check those out. Is if you took linear algebra, you know the eigenvalue and eigenmode. It's just basically taking the matrix that constitutes your system of equations and finding the eigenvalues and eigenvectors, and that will give you the frequencies of interest. So in this case, we found 10 eigenmodes, and all of them will give you different results. So it's important that you go ahead and analyze what that means. So you have one of the eigenvalues is going to show that you have a maximum deformation right here with a maximum of 115 millimeters based on the displacement that you the forces that you applied, which is 100 newtons. Um, you can check the von Mises stress, which is a magnitude of all the stresses in each direction, x, y, and z. But you can see all the other eigenvalues. Okay, so if you want to do a frequency study, this is the type of answer that you get, is the eigenmodes, and then you can go ahead and check. You can input that file to Abacus or other software and check at what frequencies these eigenvalues occur. But if not, you can just go back and do a static analysis or time-dependent analysis to see how long it takes to change temperature from ambient to, say, 75 degrees Celsius. All right, so this is how you do your analysis importing a part.